So next important topic is necessity of alloying. Necessity of alloying means so before going the discussing about the necessity. So first of all, what is alloying and why alloying is necessary, and what are the various types of alloyings, what are the material properties which affects due by the alloying, and what are the various applications of alloyings, so and also properties of alloys. So everything we need to discuss about this. So one by one we have to summarize. So first one is alloying. So alloying is the process of combination of two or more elements to form a new material with improved properties. So this is nothing but a alloying. So generally why alloying is necessary? Basically pure metals have limitations in terms of their strength, corrosion resistance, and other properties. So this is also one important thing. So alloying can improve the properties of metals, such as its strength, corrosion resistance, and ductility. So and it can create new materials. That means alloying can create new materials with unique properties that are not found in a pure metals. Okay. So and alloying can reduce the cost. So you can reduce the cost of material by using the cheaper elements. So these are the main important factors of alloying. So that's why we are doing alloying concept. Okay. And coming to the main important properties of alloys. So basically alloys have various properties that make them useful for different applications. So generally we can consider mechanical properties, corrosion resistance, electrical and thermal properties, magnetic properties. One by one we need to discuss about this. First one, mechanical properties. So mechanical properties in the sense strength, ductility, hardness, toughness. So strength means alloys can have higher strength than pure metals due to the presence of alloying elements. So this is the main important thing. And ductility. So here alloys can have improved ductility due to the presence of alloying elements, and alloys can have improved hardness due to the presence of alloying elements, and toughness. Alloying can have improved toughness due to the presence of alloying elements. So these are the mechanical properties. Coming to the corrosion resistance, in the sense corrosion resistance and oxidation resistance. So alloys can have improved corrosion resistance due to the presence of alloying, and oxidation resistance means alloys can have improved oxidation resistance too due to the presence of alloying elements. So this is regarding the corrosion resistant property. And next property, electrical and thermal properties. So electrical conductivity. So electrical conductivity means alloys can have improved electrical conductivity due to the presence of alloying elements. So thermal conductivity means alloys can have improved thermal conductivity due to the presence of alloying elements. So these are the main important things. And also magnetic properties, that means magnetic permeability. So alloys can have improved magnetic permeability due to the presence of alloying. So magnetic saturation, so it can be improved the magnetic saturation due to the presence of alloying. So these are the main basic important properties regarding the alloys. And coming to the types of alloying. Types of alloying means so how many types we need to consider. So So first one, solid solution alloying. So solid solution alloying involves dissolving one element into the another to form a solid solution. So that is the one type of alloying. And next one is precipitation hardening. So precipitation hardening involves creating precipitates in a material to improve its strength. And next type of alloys are intermetallic compounds. So intermetallic compounds are the compounds that form between the two metals. Next, ceramic metal composites. So ceramic metal composites are the materials that combine ceramic and metal properties. And at last, amorphous alloys. So amorphous alloys are the materials that have a non-crystalline structure. Okay, so these are the various types of alloying. And coming to the effects of alloying present on material properties. So obviously strength. So alloying can improve the strength of material. And corrosion resistance, that means it can improve the corrosion resistance of material. Ductility, so alloying can improve the ductility of material. Electrical conductivity, so alloying can affect the electrical conductivity of the material. And next, magnetic properties. So alloying can affect the magnetic properties of a material. So these are the effects of alloying on the material properties. And at last, applications of alloying. So aerospace industry, automotive industry, construction industry, electronic industry, medical industry, everything the alloying is present. Suppose if we consider the aerospace industry, so alloying is used in the aerospace industry to create lightweight and strong materials. Okay, so automotive industry means it is used in the automotive industry to create strong and corrosion resistance materials. And if you consider the construction industry, so alloying is used in the construction industry to create strong and durable materials. Suppose electronics means alloying is used in the electronic industry to create materials with specific electrical properties. Medical industry means to create the materials with the uh, specific biocompatibility properties. So these are the various applications regarding the alloying. Okay, so this is nothing but of alloying. So next important concept is types of solid solutions. So solid solutions are nothing but these are homogeneous mixtures of two or more elements where one element is dissolved in another one. So that is nothing but a solid solution. So what are the various types of solid solution means substitutional solid solution and interstitial solid solutions. So substitutional solid solutions can occur when the solute atoms replace the solvent atoms in the crystal lattice. So it is nothing but a substitutional solid solution. That means substitutional solid solutions are formed when the solute atoms substitute for the solvent atoms in the crystal lattice. So the substitutional solid solutions are formed when the solute and solvent atoms have similar atomic sizes or electronegativity and valencies are similar. So in that stage the substitutional solid solution can form. So this is the condition for the formation. And examples like copper nickel, AgAu, FeCr, these are the various examples of substitutional solid solutions. The main properties which have improved strength, corrosion resistance and ductility when compared to the pure metals. So that's why these type of solid solutions we are using. And next one is the interstitial solid solution. So these solutions occur when the solute atoms occupy interstitial sites in the crystal lattice. That means these are formed when the solute atoms occupy interstitial sites in the crystal lattice. So the main condition for formation is these are formed when the solute atoms are much smaller than the solvent atoms. Here solute atoms are much smaller than the solvent atoms. This is the condition for the interstitial solid solution. The main important properties for this which can improve the strength, hardness and wear resistance when compared to the pure metals. So examples like iron carbon, CuH, TiO. So these are the examples of interstitial solid solution. The main similarities like both substitutional and interstitial solid solutions are homogeneous mixtures of two or more elements. So the difference, the substitutional solid solutions involve substitution of solute atoms for a solvent atoms, while interstitial solid solutions involve occupation of interstitial sites by solute atoms. So this is the difference. The both substitutional and interstitial solid solutions are important for creating the materials with improved mechanical various properties. So this is nothing but types of solid solutions. Of empirical rules that predict the formation of solid solutions. So the first rule is atomic size. So here the atomic size of the solute and solvent atoms should not differ by more than 15%. So if the atom size difference is too large, it can lead to immiscibility or formation of intermetallic compounds. Okay, so immiscibility means I have explained in the lecture session. Please go through the notebook. So examples are nothing but copper nickel system, where the atomic size difference is of about 2%, which forms a solid solution. So this is the rule 1. That means atomic size of solute and solvent atoms should not differ more than 15%. And next rule is electronegativity. So the electronegativity of the solute and solvent atoms should be similar. So if the electronegativity difference is too large, it can lead to the formation of ionic bonds or immiscibility. So AU system, where the electrical negativity difference is small, which forms a solid solution. This is one example. And next rule is valency. So here the valency of the solute and solvent atoms should be similar. So this is the rule. So if the valency difference is too large, it can lead to immiscibility or the formation of intermetallic compounds. So iron chromium system, where the valence difference is small, which forms a solid solution. This is one example for this defining the valency. And rule 4 is nothing but a crystal structure. The crystal structure of the solute and solvent atoms should be similar. So if the crystal structure is different, it can lead to the immiscibility or formation of intermetallic compounds. So if you consider the example copper nickel system, so where both have FCC crystal structure, which forms a solid solution. So this is nothing but a Hume-Rothery rules. So the main important here which predicting the solid solution formation, that means it helps predict the formation of solid solution. And it understanding the alloy behavior, that means it helps understanding the behavior of alloys and their properties. And it can designing the new alloys, that means Hume-Rothery rules helps for designing new alloys with the specific properties. So these are nothing but Hume-Rothery rules. So next concept is Intermediate Li phases. Intermediate Li phases are the compounds that form between two or more metals. So the intermediate Li phases are the compounds that form between two or more metals with a specific stoichiometry and crystal structure. So the main characteristics, the intermediate Li phases have a fixed composition, crystal structure and properties. What are the types of intermediate Li phases? Intermetallic compounds, Leaves phases, sigma phases. So intermetallic compounds are the intermediate Li phases that form between two metals with a specific crystal structure. So it is nothing but a intermetallic compounds. So Leaves phases means these are intermediate Li phases that forms between two metals with a specific crystal structure. Sigma phases are nothing but intermediate Li phases that forms between two metals with a crystal structure. These are the various types of intermediate Li phases: intermetallic compounds, Leaves phases, sigma phases. So what is the importance of this intermediate Li phases means? So which can improve the properties. Intermediate Li phases can improve the properties of an alloy, such as its strength, corrosion resistance and ductility. So and high temperature applications, that means intermediate Li phases are often used in high temperature applications such as in jet engines and gas turbines. So and also electronic applications, intermediate Li phases are used in electronic applications such as in semiconductors and superconductors. Some examples of intermediate Li phases: nickel aluminum. So here it is an nickel aluminum is an intermetallic compound that forms between nickel and aluminum with a specific crystal structures. Titanium aluminum, so Fe3C. So these all are the intermetallic compound that forms between two elements, crystal structures. So at last the concept is electron compounds. So electron compounds are a type of intermediate Li phase that forms due to the interaction of electrons. So electron compounds are intermediate Li phases that forms due to the interaction of electrons with a specific crystal structure. So these electron compounds have a fixed composition, crystal structure and properties. Some examples: copper zinc, AgMg, AuCd, that means CuZn, copper zinc. Electron compound forms between copper and zinc with some specific crystal structure. AgMg, that means silver and magnesium, in between forms between silver and magnesium. And AuCd, one example, gold and cadmium. So the electron compound that forms between gold and cadmium with some specific crystal structure. So these are some examples of electron compounds. So it also improved properties. Electron compounds can improve the properties of an alloy, such as its strength, corrosion resistance and ductility. And high temperature applications, electron compounds are often used in high temperature applications such as in jet engines and gas turbines. Electronic applications, so electronic applications such as semiconductors and superconductors. So this is nothing but a electron compound and its importance. So by this I can conclude this unit 1 portion. So I hope